we're going to talk a little bit about how graphs relate to their equations. So say you have a polynomial function. I'm just going to make up a little quadratic one, x squared plus 6x plus 8. And if you think about it, it's equivalent to its factored form. It's going to be easiest to think about this if we have factors. What that factored form tells us is if you think about it being equal to 0, x equals -4 would be a 0, and x equals -2 would be a 0. Those would also be the x-intercepts on my graph, since they would be points where if I plug in x equals -4, I get 0, and x equals -2, I get 0. So those statements essentially all tell you the same thing, but you can think about the factor of your polynomial, you can figure out what its zeros are, what its x-intercepts are, and you'll eventually be able to kind of sketch a graph of it, which is what we're sort of working towards. So your factors, or the roots associated with those factors, zeros associated with those factors, have what's called a multiplicity, which is basically how many times that factor appears in your polynomial. So this one, 2 would be a 0 with multiplicity of 3. And 3 would be a 0 of multiplicity 1. So those are two distinct roots of my polynomial, 2 and 3, but there are really 4 if I count my multiplicity. 2 occurs 3 times, 3 factors of it, and 3 occurs once. So we're going to write a polynomial that meets some requirements. That multiplicity of 2 goes with just 3, by the way. So if I know my zeros, we can figure out some of the factors that have to be part of my polynomial. So if I have a 0 of 1, that means x minus 1 has to be a factor, because if x minus 1 is going to be equal to 0, x equals positive 1 to make that happen. If x equals -2 is a 0, then x plus 2 has to be a factor. So you're kind of thinking about what do I have to do to my 0 to get it to be equal to 0. And since 3 has a multiplicity of 2, it has to have that factor occur twice or be squared. The question says to write one of least possible degree, so that means don't have it be a higher degree polynomial than necessary, so don't change the multiplicities to anything higher than 1 on the other two factors. And you could also have a value of anything multiplied out in front to stretch or shrink it. We are gonna use our graph to estimate some of our real zeros. So one thing that we know is zeros are places where my y value is equal to 0, my output is, and it's what x values make that happen. So if I look at my x-intercepts on my graph, my zeros are 2 and -3. And then I am supposed to write the equation of a cubic function that would have these same roots or zeros. So there's a few options I could do. Okay, there's technically an infinite number of options I could do for my cubic function, but it's going to have some properties. It's going to have factors that make -3 and 2 my zeros. So x plus 3 and x minus 2 are going to have to be my factors that are included in this. And then actually, the multiplicity of my factors is important. So that's only degree 2 right now because it has x raised to the first power in it twice. If you look at the x-intercept of -3, it doesn't actually cross my x-axis there. It just like touches it and bounces back. That means that factor actually has to have an even multiplicity, kind of like, quadratics are x squared and they make that same little shape. If you were to think about zooming in, they're an even multiplicity. So this factor of x plus 3 has to have an even multiplicity, like 2, 4, 6. My multiplicity on the 0 of 2 has to be odd because my graph actually crosses at that x-intercept. It doesn't like touch it and bounce back. So those tell you if your degrees on your factors have to be even or odd. So x plus 3 needs to be even, so squared, and x minus 2 has to be odd, so to the first, you can't go higher, otherwise it wouldn't be cubic, because if you think about it, that has 3 factors, x plus 3 times x plus 3 times x minus 2, so if you multiplied it all out, you'd get x to the third. So there is this fancy theorem, it's kind of important, called the fundamental theorem of algebra. And what it says is that any polynomial of degree n has n roots. So if I have this degree 4 polynomial here, it's going to have 4 roots, or 4 zeros. If you have a polynomial that's like, say, x to the second plus 2x plus 1, that's degree 2, so it's going to have 2 roots. X to the 71st would have 71 roots. They might not be distinct, might have 71 factors that are the same, but it's got 71 roots. Now, one thing that when we relate these to graphs, you need to recognize is that only real roots can be seen on a graph as the x-intercepts. So you might have a graph of a degree 71 polynomial that doesn't have 71 x-intercepts because some of its zeros are going to be non-real complex numbers. Alright, let's use this graph to solve an equation. So actually solving equations by graphing is one of my favorite ways to solve them. It makes it really super easy when you have a nice graphing app and you can just have the computer do some of the work for you. So for this equation, I'm looking at x values that make y equal to 0. So really, I'm kind of finding my roots here, the real ones. So if I look on my graph to see what points have y values of 0, I know I missed putting a dot on that one on the right, but I'll get it. So looking at the x-coordinates of these points to figure out our solutions to this equation, the x values that give us y values of 0 are those 5 values right there. So we've got 5 real solutions that we can see represented as the x-intercepts on our graph. So if we've got 5 real solutions, that means we have some complex, non-real complex solutions that we can't see on our graph because the fundamental theorem of algebra says that your degree 7 polynomial equation, which this is, should have 7 total solutions, and we can only see 5 represented as x-intercepts on our graph. So that means the missing 2 solutions have to be non-real complex numbers as our solutions, like maybe 2i or something like that.